Okay, still working on the final paper, the final work, and I just threw my papers away. Whatever, we're supposed to be working on this derivative equation, and we've got it written there, and it's asking how many ways can we do this. I know it's first order linear, but beyond that, just doing the Laplace is fine enough, since it states specifically that we can do that. But I went ahead and did it, which is a pain. The first thing we do is perform the Laplace transformation on both sides, and we can separate that out once we do that. And I've got since we can we can take these out because we've been told we can. So 1 times Laplace of y, or the function of y of t minus y of 0 plus the 3 times the y of s, again the function y of s, or y of s, sorry, function of y of s. That's what we're doing. We're transforming this from a function of t to a function of s. But anyway, function of y of s, and then 13, and this is a value from the book, obviously. We got 2 over s squared plus 4, 2 squared. So then I'm putting like terms together. We've got s times y of s, and 3 times y of s minus 6, because this is 6. This value is 6 from up here. So I move that over there. But then I just added it on this side. So that's 13 times 2, 26. Factor. And equals that. And then I just went ahead and, as you can see, at 1 over 3 plus s, that's 1 over 3 plus s. And that gives us that when we simplify it. So the Laplace of y, or y of s, the big Y of s, is equal to this. So we want to take the inverse Laplace, which I'm doing here on the whole thing. And to do that, we start our partial fractions. I split it up, so we've got our equation there, but we want it to be in the form of this as plus b over s squared plus 4 plus the c times the s plus 3. Multiply all that out, and then we get, since this is the same bottom, we know that the top must be the same, and that's what I've got written here. This is the top, 6s squared plus 50, as plus b times s plus 3 plus c times s squared plus 4. Substitute in the minus 3, and the reason we're using minus 3 is because of our 3 plus s, which we know is root before. And that is helpful for us because it zeroes out this term, and that's just substituting minus 3 in for s. So a times minus 3 plus b times minus 3 plus 3, that all is 0. C times minus 3 squared plus 4, so 13 times c equals 104, c equals 8. Back to this one. So as squared plus 3as plus bs plus 3b plus 8s squared plus 32 equals our 6s squared plus 50. Separate that into a system of equations, and we can see that b equals 6, a equals minus 2. And what that means is that now we know that our fractions are these two, minus 2s plus 6 over s squared plus 4, and 8 over s plus 3. And that's just because we go back and we substitute in a, b, and c in their respective spots. So we're putting that in, the values in for a, b, and c, and then that in for this. And then we're going to take the inverse Laplace of it, which is what I did. So obviously the inverse Laplace of the Laplace is just y. And I split this out a little bit differently. 6, I don't know why I sorted them, but 6 over s squared plus 4 minus 2 over s squared plus 4 plus 8 over s plus 3. Taking out numbers to make it work. These are just using the inverse functions, Laplace transformations that are in the book on like 285. 3 times this, so 3 sine 2t plus this one. 8 we take out, so it's 8 times 1 over s plus 3, or then 8 times e to the minus 3t s minus minus 3, and then 2 minus 2 times the Laplace of s over s squared plus 4, so minus 2 cosine 2t, and then because I like switching around the order of the terms a lot, y equals minus 2 cosine 2t plus 3 sine 2t plus 8 to the minus 3t, and that's the final answer.